ready.
Longshot's here to crack the solar system open like an egg. We're building a multi-injection gas accelerator to throw massive vehicles to orbital velocities and put them directly into orbit.
The current project we're working on what's called the Glowrider. It's basically a model of the hypersonic vehicle that will eventually be shooting out of the accelerator. The engineers have a MATLAB setup that automatically generates a Glowrider for a particular Mach level. Basically, each Mach level has a different shape Glowrider that is associated with it. That outputs a 3D shape, and then I can convert that to a SolidWorks part, and from there we can map out the surface so that we can produce it from sheet metal. This is a small scale version, which fits in our 6-inch accelerator, and we're basically scaling it up. So we have the bottom here, this flange is going to get tipped up, so it's going to be 45-degree angle like that, and then we have these other panels, so those get arched over the top and then riveted onto this flange.
We have an internal tool that we can take given design parameters or flight conditions that we'd like to model around. And this one was just a quick example. I believe we chose Mach 6 as the starting point, and then we knew we wanted a certain amount of area inside. So it's rounded at the top right now to ensure that we've got a larger internal volume for, in the future, onboard telemetry, flight computers, whatever payload is desired to be in there.
We were making some small versions, and there's some initial kind of legwork to figure out what gauge of metal should we use, because we don't want it to be too heavy, but we also want it to be strong. We also need our current tooling to be able to handle it. So I did a couple test pieces, and it seemed like 22 gauge was just fine for what we need, and much lighter, much cheaper, so went with that route. Pretty much every project you work on, you have to either make a tool or modify a tool to get it to do what you want. Like, for example, the English wheel, we could have bought one, but it would have taken too long to ship here. So we bought the wheel parts, and then we had metal around, so we just made the English wheel, and that worked pretty great.
This is what we call the compression surface. So basically your lifting surface. The important part is that we could trace a line right along this leading edge all the way to eventually the nose, and it would measure exactly our expected shock angle given our nose geometry. If we were to look at this like a plane, this would be your wings, these corners, and we can decide how much of it we want attached to the actual shockwave and the compressed flow there to dictate if we need more lift. But if we want more lift, that's going to induce more drag, so it just has to be designed around that. That'll be all material selection. The shape right here, like the reason it kind of chamfers down is, one, to make sure that it's actually manufacturable, and two, we don't need the whole thing attached to the flow. That would just be, and at that point you're just shooting a cone. Far too much drag. We basically say, hey, what percentage of our wing do we want attached to the flow to generate our lift? And then it goes from there. So this is a very, very, very low percentage right now to make sure that we have a nice like lift to drag ratio. So we can see it then domed out a little bit over here to make sure we could have some sort of internal sizing. Again, you know, we're going to want to launch satellites. We're going to be moving on to the design and analysis phase as the months progress. So right now, just having a starting point for the tool and seeing it kind of come to life is actually being really cool.
I am completely irrationally excited by this. This is the first time we've given form to a bunch of ideas that we've had for a long time about how to build this glide vehicle that can start in the lower atmosphere at crazy high speeds and exit slightly less crazy high speeds, the upper atmosphere. What we're doing is not the normal approach for getting things to fly at these speeds, and so it's important to show people what you intend to do so they can understand it. You just have to show. You can only tell so much. So building this vehicle behind us is a really, really important part of conveying the highest level vision of the company, and also just like, what are we going to do in the next year or two? What could we build? What will it look like? What kind of cargo could it carry? We're telling the story of that system. We're going to build a big physical model of it that can actually get thrown out of the accelerator, and also we should be able to fit it inside of the accelerator that we're building in soon, which I'm really excited about too. Stay tuned for what's coming next. My hope is that our next major update is coming to you from the beautiful big sky country of